What if everything we thought we knew about life in the universe was just the tip of the cosmic iceberg? For centuries, humanity has gazed at the stars, whispering the same burning question: are we truly alone? Tonight, that question might finally have an answer. Scientists have uncovered not one, not two, but 30 jaw-dropping discoveries scattered across the cosmos, each one a potential clue in the greatest mystery of all time. From distant exoplanets with atmospheres thick with the chemical fingerprints of life, to enigmatic signals that defy all natural explanations, the evidence is piling up, and it's pointing to something extraordinary. Picture this: a world where oceans slosh beneath the icy crust of a moon in our own solar system, where plumes of water vapor burst into space like a beacon calling out to the universe. Or consider the exoplanet, where telescopes have detected bizarre, repeating patterns in the light filtering through its atmosphere, patterns that match what we'd expect from vast, living forests or even industrial civilizations. These aren't scenes from science fiction. They're real, documented, and waiting for us to piece together. The universe isn't just vast and empty. It's humming with possibilities, and every new discovery brings us closer to the moment when we finally hear a cosmic whisper back. This isn't just about aliens, it's about rewriting the story of life itself. What if life isn't some rare accident, but a natural part of the universe's rhythm, a rhythm we're only now beginning to hear? From the depths of Martian caves to the swirling storms of distant gas giants, the evidence is mounting in ways that would have seemed impossible just a decade ago. And that's why today we're diving into the 30 most electrifying cosmic breakthroughs that could shatter our understanding of existence. Some of them will make you gasp. Others might keep you up at night, but one thing's for sure: by the end, you'll never look at the night sky the same way again. So, are you ready to explore the discoveries that could change everything? Let's begin. Venus, our closest planetary neighbor, just tossed scientists a curveball that rewrote the playbook on where we might find life. In 2020, researchers announced something that shouldn't have been there: a phosphine gas floating high in the planet's thick sulfuric clouds. On Earth, this stinky, toxic gas has one glaringly obvious source: microbes, anaerobic bacteria, the kind that thrive in places without oxygen like swamps, and your gut churn it out constantly. So when telescopes picked up its unmistakable fingerprint in Venus's atmosphere, the science world practically erupted. Here's why it's such a bombshell. Venus's surface is a hellscape hot enough to melt lead, crushed under an atmosphere 90 times thicker than ours with clouds of sulfuric acid. Not exactly prime real estate. But up in those clouds, about 30 to 40 miles above the surface, temperatures and pressures are eerily Earth-like, and that's exactly where the phosphine sits. The problem: every known non-biological process, volcanoes, lightning, photochemical reactions, should produce at most a tiny fraction of what was detected. So unless Venus is hiding some exotic chemistry we've never seen before, there's a chance, however slim, that something alive is making it. Of course, science loves a good debate, and this one got heated. Critics pointed out possible errors in the data or overlooked abiotic processes. Follow-up studies scrambled to confirm or debunk it, with some teams failing to detect phosphine at all. Then, in 2023, another group not only verified its presence but pinned down potential variations in concentration, hints that something dynamic, maybe even seasonal, is happening up there. The plot thickens when you realize Venus's clouds contain other bizarre anomalies, like mysterious dark patches that absorb ultraviolet light in ways we still can't explain. Could those be organic compounds or even floating microbial communities? The implications are staggering. If life exists in Venus's clouds, it would mean biology isn't just a quirk of Goldilocks planets, it's a fighter, capable of thriving in the most hostile corners of the cosmos. Suddenly, every acid-clouded exoplanet becomes a candidate. But here's the real kicker. We might not have to wait decades for answers. Proposed missions like NASA Da Vinci and the private-backed Venus Life Finder aim to plunge probes directly into those clouds within the next 10 years, sniffing for chemical clues. Imagine if they find Cell's alien life right next door. It's the kind of discovery that wouldn't just rewrite textbooks, it would redefine humanity's place in the universe. Jupiter's moon, Europa, has always been a tantalizing enigma, shrouded in ice but hiding what might be the most promising habitat for alien life in our solar system. Then, in 2013, the Hubble Space Telescope caught something extraordinary: gigantic plumes of water vapor erupting from Europa's frozen surface, shooting more than 100 miles into space. It was as if the moon itself was sending us a message: dig deeper. These plumes aren't just random geysers, they're the smoking gun for a vast global ocean buried beneath Europa's icy shell, one that could hold twice as much liquid water as all of Earth's oceans combined. And here's where it gets even more intriguing. On Earth, we've found entire ecosystems thriving in the darkest depths of our oceans, clustered around hydrothermal vents where superheated, mineral-rich water spews from the seafloor. These vents don't just support life, they fuel it without a single ray of sunlight. Europa's ocean, warmed by the gravitational tug-of-war of Jupiter's immense pull, could be doing the exact same thing. But how do we know these plumes are connected to a hidden ocean? The evidence is in the spray itself. Spectroscopic analysis revealed traces of sodium chloride, a plain old table salt mixed in with the water vapor. That's a huge clue because salt suggests the water has been in contact with rock, likely at the bottom of Europa's ocean, leaching minerals just like Earth's seas do. Even more compelling, some of these plumes seem to erupt near long, dark cracks in Europa's ice, where tidal forces might be squeezing the subsurface ocean upward like toothpaste from a tube. The implications are staggering. If Europa's ocean has hydrothermal activity, it could be a paradise for extremophiles microbes that thrive in conditions we once thought were uninhabitable. And if life can survive there, bathed in radiation and sealed under miles of ice, it raises the spine-tingling possibility that similar moons, like Saturn's Enceladus or even distant Pluto, might harbor their own hidden biospheres. NASA Europa Clipper mission, launching in 2024, is designed to hunt for answers. It won't land, but it will skim just 15 miles above the surface, analyzing plume material and mapping the ice shell in unprecedented detail. Imagine if it finds organic molecules or, better yet, chemical imbalances that hint at active biology. We could be on the verge of discovering that life isn't an earthly fluke. It's a cosmic inevitability, bubbling up wherever there's liquid water, energy, and time. Europa isn't just a frozen moon. It might be a living world whispering to us across the void. While Europa steals much of the spotlight, Saturn's tiny moon Enceladus delivers one of the most jaw-dropping revelations in the search for alien life. Proof of an active, habitable ocean right in our cosmic backyard. The Cassini spacecraft, during its 13-year tour of the Saturn system, spotted something no one expected: towering geysers near Enceladus' south pole, blasting water ice and organic molecules hundreds of miles into space. But the real bombshell came when Cassini dove through these plumes, tasting their contents like a cosmic sommelier. The results: hydrogen gas, lots of it, mixed with silica nanoparticles. On Earth, that combination screams one thing: hydrothermal vents churning away on the seafloor. This isn't just a hunch. The chemistry matches perfectly with what we see at hydrothermal vents in Earth's oceans, where superheated water reacts with rock to produce hydrogen, a key ingredient for certain microbes that thrive in those extreme environments. These organisms don't need sunlight or oxygen. They survive by combining hydrogen with carbon dioxide in a process called chemosynthesis, forming the base of entire ecosystems. If Enceladus' hidden ocean has the same recipe, life might not just be possible, it could already be thriving there in the dark. What makes Enceladus so special isn't just the presence of water. It's the sheer energy of its system. The moon gets squeezed and stretched by Saturn's gravity, generating enough internal heat to keep its subsurface ocean liquid and its vents roaring. Cassini even detected organic molecules like methane and formaldehyde in the plumes, the building blocks of life as we know it. And here's the kicker. The silica particles Cassini found are the exact size and composition we'd expect if hot water was dissolving rock deep below, just like at Earth's vents. The implications are staggering. If life can emerge around hydrothermal vents on Earth, why not on Enceladus? This tiny moon, barely 300 miles wide, checks every box on the habitability checklist: liquid water, organic material, and a steady energy source. Future missions like NASA's proposed Enceladus Orbiter could one day orbit the moon, sampling its plumes for amino acids or even cellular structures. Imagine if we found evidence of microbial life there, proof that biology isn't bound to Earth's Goldilocks zone, but can ignite anywhere there's water, chemistry, and time. Enceladus isn't just a frozen speck. It's a beacon shining a light on the cosmic potential for life in the unlikeliest of places. Mars has always been Earth's mysterious twin, a world that might have once resembled our own blue planet but now lies frozen and arid. Yet against all odds, streaks of darkness slither down its rusty slopes each summer, vanishing when temperatures drop. These eerie features, called recurring slope lineae, were first spotted by orbital cameras in 2011, and they've been fueling scientific debates ever since. What makes them so fascinating? Their timing suggests they're not just dry dust slides. They behave exactly how flowing liquid water would, the leading theory. Super salty brine. Mars' surface is far too cold for pure water to stay liquid, but mix in loads of perchlorate salts, a type of chemical compound we've actually detected in Martian soil, and suddenly water can remain fluid at temperatures as low as -90 degrees Fahrenheit. These brines wouldn't look like Earth's rivers. They'd be thick, sludgy flows creeping just beneath the surface, darkening the soil as they seep through. The fact that these streaks reappear in the same locations year after year hints at an underground reservoir, possibly fed by melting ice or deep aquifers. But here's where it gets wild. If there's liquid water, however briny, could anything survive in it? On Earth, we find microbes thriving in similarly harsh places, like Chile's Atacama Desert or Antarctica's dry valleys, where water is scarce and packed with salt. Some extremophiles don't just endure these conditions, they rely on the salts to prevent their cells from freezing solid. If Martian microbes exist, they might employ the same strategy, lying dormant for most of the year and springing to life when the streaks briefly flow. Not everyone's convinced, of course. Some scientists argue these features could be dry granular flows, where sand and dust slide downhill without any liquid involved. But recent experiments show that even small amounts of brine mixed with Martian soil could create the exact patterns we observe. And in 2015, NASA's Mars Reconnaissance Orbiter detected hydrated salts right on the streaks, minerals that literally trap water molecules in their structure. That's about as close to a smoking gun as we've gotten. The stakes couldn't be higher. If these streaks truly mark spots where liquid water emerges today, they'd be prime targets for future landers, places where we might finally answer whether life ever took root on Mars. Imagine a rover scooping up damp soil from one of these flows and finding microscopic survivors clinging to existence in a world we thought was dead. It would prove that life isn't just stubborn, it's universal, blooming wherever there's even the slimmest chance to survive. Mars' dark streaks aren't just geological curiosities. They could be the trails leading us to our first encounter with alien biology. Saturn's largest moon, Titan, isn't just another frozen world. It's a bizarre, mirror universe version of Earth, complete with rivers, lakes, and even rain. But here's the twist, none of it is water. Instead, Titan's valleys are carved by liquid methane. Its clouds drip hydrocarbon showers, and its vast lakes shimmer with ethane under a hazy orange sky. This isn't just exotic geology, it's a playground for the most radical possibility in astrobiology, life that doesn't need water at all. What makes Titan so tantalizing is its sheer chemical abundance. When the Cassini spacecraft mapped its surface, it revealed lakes like Kraken-Mer, larger than Earth's Caspian Sea, filled with liquid methane and ethane. But the real shocker came when scientists realized these lakes aren't stagnant. They evaporate, form clouds, and rain back down in a cycle eerily similar to Earth's water cycle. And within this alien solvent, complex organic molecules like benzene and hydrogen cyanide swirl, the kind of building blocks that, on Earth, would be prime ingredients for life. Here's where it gets speculative and thrilling. On our planet, life relies on water as a solvent, a medium for chemical reactions. But what if, in Titan's frigid -290°F chill, life evolved to use methane instead? Imagine organisms with cell membranes made not of lipids but of tough, flexible compounds like acrylonitrile, which could withstand the cold. Their metabolism might rely on breaking down acetylene or ethane, breathing hydrogen instead of oxygen. It's not as far-fetched as it sounds. Lab experiments have already shown that simulated Titan conditions can produce amino acids and nucleotide bases, the raw materials of biology. Even more compelling are Titan's magic islands, mysterious bright spots in its lakes that appear and vanish on radar scans. Some scientists suggest these could be floating clumps of organic solids like wax on a tar pit. Others wonder if they might be something far more dynamic, perhaps even buoyant structures created by life itself. And beneath Titan's icy crust, a subsurface ocean of water and ammonia adds another layer of intrigue. Could there be two separate biospheres, one water-based below, one methane-based above, existing on the same moon? The upcoming Dragonfly mission, set to launch in 2027, aims to land a drone-like rotorcraft on Titan's dunes, sniffing the air and soil for chemical clues. If it detects molecules that defy natural equilibrium, say, an unexpected depletion of hydrogen or acetylene at the surface, it might hint at something consuming those compounds. Titan forces us to rethink the very definition of life. If biology can emerge in a world without liquid water under skies thick with organic smog, then the universe might be far stranger and far more alive than we ever dared dream. The exoplanet K2-18b wasn't supposed to be this interesting. Orbiting a dim red dwarf star 120 light-years away, this world is nearly 9 times heavier than Earth, a category scientists call super-Earth. But in 2019, the Hubble Space Telescope revealed something astonishing. Its atmosphere isn't just a hazy mix of hydrogen and helium like most gas dwarfs. It's brimming with water vapor, thick enough to form clouds and possibly even rain. And here's the real kicker. K2-18b sits snugly in its star's habitable zone, where temperatures could allow liquid water to pool on its surface. But how does a planet this massive even have an atmosphere we can study? The answer lies in its star. Red dwarfs are cooler and smaller than our Sun, which means their habitable zones sit much closer in. K2-18b orbits its star in just 33 days, close enough for Hubble to catch the starlight filtering through its atmosphere during transits. That light carried fingerprints of water vapor along with hints of hydrogen and helium. The presence of water alone is groundbreaking, but the real magic lies in what it implies. Calculations suggest that under all that gas, K2-18b might have a rocky core. And if temperatures are just right, that core could be capped by a global ocean, not unlike Europa's subsurface sea, but with one crucial difference. Instead of being trapped under miles of ice, this ocean might sit beneath a thick, humid atmosphere, with rain cycling between sky and surface. Some models even propose that the planet's high pressure could create exotic states of water like supercritical fluid, a bizarre form where liquid and gas blur together. Of course, not everyone's convinced K2-18b is a water world. Its sheer size means gravity would be crushing, and that hydrogen-rich atmosphere might create a furnace-like greenhouse effect. But here's where it gets fascinating. In 2023, new data from the James Webb Space Telescope detected traces of dimethyl sulfide in its atmosphere, a molecule that, on Earth, is almost exclusively produced by living organisms like phytoplankton. The finding is still unconfirmed, but if real, it raises a tantalizing question. Could something be alive in those alien clouds? Future telescopes, like the upcoming Ariel mission, will scrutinize K2-18b's atmosphere for more biomarkers. Imagine if they find oxygen alongside that water vapor or methane in concentrations that defy geology. This isn't just about finding another wet planet. It's about rewriting the rules of where life can exist. Super-Earths like K2-18b are among the most common planets in the galaxy. If even one of them harbors life, the universe might be far more crowded than we ever dreamed. The TRAPPIST-1 system is like a cosmic Russian nesting doll, 7 rocky worlds, each eerily close in size to Earth, all crammed into orbits tighter than Mercury's around their dim red star. Discovered in 2017, this compact family of planets shattered expectations, proving that Earth-like worlds don't just exist, they can come in packs. But the real stunner, 3 of them orbit smack in the middle of the star's habitable zone, where temperatures could allow liquid water to pool on their surfaces. This isn't just a lineup of exoplanets, it's a laboratory for testing how common life might be across the cosmos. What makes TRAPPIST-1 so special starts with its star, an ultra-cool dwarf so faint it shines with just 1/2000th of our sun's brightness. But that dimness is a gift for planet hunters. Because the star is so cool, its habitable zone snuggles in close, meaning planets there orbit in days, not years. That proximity lets telescopes watch for tiny, rhythmic dips in starlight as each planet transits, revealing their sizes, masses, and even hints of their atmospheres. And the data paints a jaw-dropping picture. All 7 worlds are roughly Earth-sized, with densities suggesting rocky compositions like ours. The 3 Goldilocks planets, TRAPPIST-1e, F, and G, are where things get wild. Models suggest E, the most Earth-like, could have a climate eerily similar to ours, while F and G might be icy worlds with subsurface oceans or steamy, water-rich atmospheres. But here's the twist. These planets are likely tidally locked, with one face forever turned toward their star and the other shrouded in eternal night. That might sound like a deal-breaker for life, but nature loves surprises. On Earth, we've found organisms thriving in pitch-black caves and sun-scorched deserts. A tidally locked world could host life in the twilight strip between day and night, where temperatures might be just right for liquid water, and who knows what else. The real game-changer, though, is the hunt for atmospheres. In 2023, the James Webb Space Telescope trained its sights on TRAPPIST-1b, the innermost planet. While it's too hot for life, Webb's analysis ruled out a thick, Venus-like atmosphere, proving we can study the air around Earth-sized exoplanets. Now, scientists are scrambling to point Webb at E, F, and G, searching for traces of water vapor, carbon dioxide, or even methane gases that could hint at oceans, volcanoes, or biology at work. The implications are staggering. If just one of these worlds has an atmosphere with the right chemistry, it would mean Earth isn't some rare fluke. It would mean the galaxy could be littered with habitable real estate, orbiting the countless red dwarfs that make up 75% of all stars. TRAPPIST-1 isn't just a curiosity, it's a beacon lighting the way toward answering humanity's oldest question: are we alone? And with every new observation, we're one step closer to finding out. When Oumuamua streaked through our solar system in 2017, It wasn't just the first known visitor from another star system, it was an enigma wrapped in cosmic riddles. Shaped like a flattened cigar and tumbling unpredictably, this interstellar traveler defied every expectation, but the real mystery wasn't its odd form. It was the way it accelerated as it raced away from the sun, as if pushed by an invisible force. At first, scientists assumed outgassing, the same process that makes comets speed up when sunlight vaporizes their icy surfaces, creating a natural jet effect. But here's the catch: Oumuamua showed no visible coma or tail, the telltale signs of outgassing, no dust cloud, no icy particles sparkling in its wake. Just that strange, stubborn acceleration. Researchers scrambled for explanations, proposing everything from hydrogen ice sublimating in deep space, a process never observed before, to the object being a porous dust bunny of cosmic debris, light enough for sunlight alone to nudge it along. Then came the curveball. Astrophysicist Avi Loeb suggested an even more radical idea. What if Oumuamua wasn't a natural object at all? His controversial hypothesis argued the acceleration matched what we'd expect from a lightweight solar sail, an artificial structure designed to catch radiation pressure like a ship harnessing the wind. The shape fit too. A flat, thin sail would explain why Oumuamua reflected light so oddly as it spun. Suddenly, the conversation exploded. Were we looking at a discarded piece of alien technology drifting between the stars? The scientific community pushed back hard, pointing out that extraordinary claims require extraordinary evidence, and Oumuamua's brief, blurry visit left too many gaps. But even critics admit the object's behavior is bizarre. New studies suggest exotic ices like nitrogen could explain the acceleration without invoking aliens, while others speculate it might be a shard of a Pluto-like planet, blasted into interstellar space by some ancient collision. The truth is, we may never know for sure. Oumuamua is now beyond the reach of our telescopes, a ghost fading into the void. But its legacy lingers, whether it was a cosmic iceberg, a fragment of an alien world, or something even stranger. It forced us to confront a humbling reality. The universe is capable of crafting phenomena we don't yet understand, and sometimes the most tantalizing mysteries are the ones we can't solve. Fast radio bursts have long been one of space's most electrifying puzzles, blistering blasts of energy so powerful they outshine entire galaxies for milliseconds before vanishing without a trace. But in 2016, something shifted. Astronomers detected FRB 121102, the first burst that didn't just fire once, it repeated. And not randomly, in a rhythmic pattern that defied all natural explanations. Suddenly, these cosmic fireworks weren't just anomalies. They were messages in a bottle, floating through the void with secrets we're only beginning to unravel. The plot thickened in 2020 when scientists traced one repeating burst, FRB 180916, back to a spiral galaxy 500 million light-years away. That location was a shock. Most theories had pinned FRBs on extreme environments like neutron star collisions or Magnetar's super-dense magnetic stellar corpses. But this burst originated in a calm, unremarkable region of a galaxy startlingly similar to our own Milky Way. It was like finding a fire alarm blaring in the middle of a library. The implications: either we're missing something fundamental about how these bursts form, or we're staring at something far more deliberate. Here's where it gets spine-tingling. Some bursts, like FRB 191209, spit out signals with near-perfect mathematical intervals, some repeating every 16.35 days like clockwork. Natural cosmic phenomena don't keep schedules, collapsing stars don't punch time cards, yet these bursts hum along with precision that mirrors human-engineered signals. Astrophysicists have theorized exotic possibilities: alien megastructures harvesting stellar energy, interstellar beacons guiding spacecraft, or even leakage from hyper-advanced communication networks. Harvard's Avi Loeb famously suggested they could be light sails, enormous energy beams propelling probes across galaxies. Skeptics counter that pulsars, the spinning remnants of dead stars, also emit regular pulses without aliens involved. But pulsars slow down over time as they lose energy. These FRBs, their timing stays unnervingly exact, and then there's the sheer energy. A single millisecond burst could power all of humanity for centuries. Whatever's producing them isn't just mysterious, it's operating on a scale we can barely fathom. The hunt for answers is accelerating. New telescopes like Canada's CHIME are catching dozens of bursts monthly, revealing patterns that hint at universal structures we've yet to map. Some show frequency drifts like a radio dial sliding between stations. Others have downward frequency sweeps eerily reminiscent of artificially encoded signals. With every new detection, the line between natural wonder and cosmic hello blurs further. One thing's certain, the universe isn't just speaking, it's repeating itself. And we're finally starting to listen. Just 4.2 light-years away, practically on our cosmic doorstep, lies a world that could rewrite the rules of where life can exist. Proxima Centauri b. Orbiting the closest star to our Sun, this rocky planet is roughly Earth-size and sits snugly in its star's habitable zone, where temperatures might allow liquid water to pool. But here's the twist: Proxima Centauri isn't a calm, sun-like star. It's a red dwarf prone to violent flares that can unleash a torrent of radiation with little warning. So how could anything survive on a planet constantly bathed in such fury? The answer might lie in a hidden shield, an atmosphere stubborn enough to weather the storm. Scientists initially doubted Proxima b could cling to its air for long. Red dwarfs like Proxima Centauri are notorious for their temper tantrums, blasting out ultraviolet and X-ray flares hundreds of times stronger than anything our Sun produces. These bursts can strip atmospheres bare, leaving planets as barren as Mars. But recent simulations reveal a game-changer. If Proxima b started with a thick, Earth-like atmosphere, or better yet, one richer in oxygen or carbon dioxide, it might endure. Even under relentless flares, atmospheric loss could be slow enough for life to gain a foothold. Some models even suggest that a global magnetic field, like Earth's, could deflect enough radiation to keep the planet's surface habitable. Then there's the wild card, tidal locking. Proxima b likely always shows the same face to its star, creating a permanent day side and a frigid night side. But instead of dooming the planet, this setup could forge bizarrely stable environments. The Terminator line, the twilight zone between eternal day and night, might host temperate pockets where liquid water could persist. Imagine a ring of habitability circling the planet, where organisms adapted to perpetual dusk could thrive. But the real excitement lies in our plans to visit. Breakthrough Starshot, the audacious initiative backed by Stephen Hawking and Yuri Milner, aims to send a fleet of tiny, laser-propelled probes to Proxima b within decades. These gram-scale starships would sail on light beams, reaching 20% the speed of light fast enough to arrive in just 20 years. Their mission: fly by Proxima b, snap images, and scan for atmospheric gases like oxygen or methane. If they spot the right cocktail of chemicals, it could mean biology is at work next door. Proxima Centauri b forces us to rethink what makes a world livable. A planet drenched in radiation, lashed by stellar winds, and locked in perpetual twilight might sound like a dead zone. But life, as we've learned, is relentless. If it can cling to existence here in the harshest of neighborhoods, then the cosmos might be far more crowded than we ever imagined. We could be on the verge of discovering that the nearest star to ours doesn't just host a planet, it hosts a living one. That eerie blip from the cosmos, lasting just 72 seconds but haunting astronomers for decades, has finally found its 21st century counterparts. The infamous WOW signal, detected in 1977 by Ohio State's Big Ear radio telescope, wasn't just a cosmic fluke. Its intensity, narrowband frequency, and precise hydrogen line wavelength made it the closest thing we've ever recorded to an interstellar shout. And now, new signals are echoing its bizarre signature, each one reigniting the debate: is someone or something out there tuning into the universe's grandest frequency? Take the baffling case of radio source SETI-02+14A. Detected by SETI at home volunteers in 2003, this signal pulsed at exactly 1420 MHz, the same hydrogen line frequency as the WOW signal and a prime candidate for interstellar messaging. Even stranger, it appeared to drift in a way that matched a planet's rotation, as if transmitted from a spinning world. The kicker, it vanished before researchers could pin it down, leaving behind tantalizing static and a trail of questions. Then there's BLC-1, a signal picked up in 2020 from Proxima Centauri, our nearest stellar neighbor. Unlike random cosmic noise, BLC-1 was a pure, unmodulated tone, sliding smoothly in frequency like a deliberate broadcast. While most experts eventually dismissed it as human interference, its uncanny resemblance to an engineered signal kept the conversation alive. Why are these detections so electrifying? Because they defy natural explanations in eerily specific ways. Natural cosmic radio sources like pulsars or quasars blast wide-spectrum noise or predictable pulses. But these signals, they're laser-focused, as if someone cranked a cosmic dial to the universe's most obvious channel, the hydrogen line at 1420 MHz, the same frequency hydrogen atoms emit naturally in space. It's not just a logical frequency for communication. It's a giant neon sign saying, "Listen here." Even more compelling, some of these signals exhibit what radio engineers call Doppler drift, subtle frequency shifts that match the motion of a transmitter on a rotating exoplanet. It's the kind of detail you'd expect from a civilization aiming a dish at us, not random stellar static. Skeptics argue these could be glitches, satellite interference, faulty equipment, or even microwave ovens polluting the data. But the WOW signal's enduring mystery proves how hard it is to dismiss anomalies that tick every box for artificial origin. Modern efforts like the Breakthrough Listen project are scanning millions of frequencies with AI, filtering out earthly noise to catch these whispers in the cosmic static. The next big detection might not be another fleeting blip. It could be a repeating signal broadcasting in a pattern simple enough to decode, a cosmic hello waiting in the noise. And if it comes, we'll finally have an answer to the question that's haunted us since 1977. Were we ever alone or just late to the conversation? Imagine a world not just Earth-like, but Earth plus a planet with 60% more sunlight, twice the volcanic activity, and 6 billion years under its belt to evolve life far beyond anything we know. That's Kepler 452b, a cosmic time capsule orbiting a star eerily similar to our Sun, but 1.5 billion years older. Dubbed Earth's older cousin, this planet isn't just another Goldilocks candidate. It's a glimpse into what our own world might become, or what could already be thriving in a system that's had a colossal head start. Discovered in 2015 by the Kepler Space Telescope, this ancient world sits squarely in its star's habitable zone, with a years-long orbit of 385 days, just 20 days longer than Earth. But here's where it gets fascinating. Kepler 452b's star is a near twin of our Sun, burning at nearly the same temperature and brightness. Unlike the volatile red dwarfs hosting most known exoplanets, this star's stability means its planets have likely enjoyed billions of years of calm, continuous sunlight, a luxury for any potential life. What really sets this world apart is its age. At 6 billion years old, it's had 40% more time than Earth to cook up complex biology. Consider what life on our planet achieved in just 4.5 billion years, single-celled organisms to spacefaring civilizations. Now imagine what an extra 1.5 billion years of evolution might produce. Some astrobiologists speculate that if intelligence emerged there even slightly earlier than on Earth, Kepler 452b could host a civilization with technology so advanced it borders on magic. But could such an old planet still be habitable? The answer lies in its geology. Kepler 452b is about 5% larger than Earth, which might give it more active plate tectonics, a crucial recycling system that stabilizes climates over eons. Its stronger gravity could also help retain a thicker atmosphere, shielding life from cosmic rays. Then there's the sunlight. With 60% more exposure than Earth, photosynthesis, if it exists there, might operate at staggering efficiency, fueling ecosystems of colossal scale. Of course, there are no guarantees. A planet this old could also be a cautionary tale. Its star, now entering its subgiant phase, is gradually brightening, a preview of Earth's fate in a billion years. If Kepler 452b once had oceans, they may have already evaporated under the growing heat, or perhaps life adapted, migrating to polar refuges or underground aquifers. The only way to know, next-gen telescopes like NASA's Habitable Worlds Observatory, set to launch in the 2040s, could analyze its atmosphere for signs of oxygen, methane, or even artificial pollutants, chemical fingerprints of a world that didn't just host life but mastered it. Kepler 452b isn't just a scientific curiosity. It's a mirror held up to Earth's future and a window into what might be possible when life gets a cosmic running start. If civilizations can outlast their star's youth, what might they become? The answer could already be out there, orbiting a sun that began shining before ours even ignited. The space rocks that occasionally plummet to Earth might be carrying more than just cosmic debris. They could be ferrying the very building blocks of life itself. In 1969, the Murchison meteorite crashed into Australia, scattering fragments that would later reveal something revolutionary: complex organic molecules, including nucleobases like adenine and guanine. These aren't just random chemicals, they're the ABCs of DNA, the fundamental letters in life's genetic code. The discovery sent shockwaves through the scientific community because it suggested something radical. The ingredients for biology might not be unique to Earth. They could be raining down on us from space, seeding planets across the galaxy with the potential for life. But Murchison was just the beginning. Over the decades, researchers have identified over 70 different amino acids in its fragments, many of which aren't even found on Earth. That's a smoking gun for chemistry occurring in the depths of space, far from any planet's influence. Even more compelling, these molecules show a slight excess of left-handed chirality, a mirror image preference that on Earth is a hallmark of biological activity. Could the same asymmetry exist in the cosmic clouds where these meteorites form, hinting at universal precursors to life? Then there's the Martian meteorite LH-84001, a 4.1 billion-year-old chunk of the red planet that made headlines in 1996. When scientists cracked it open, they found microscopic structures eerily resembling fossilized bacteria, complete with chain-like formations and mineral deposits that on Earth are produced by microbial activity. The debate that followed was explosive. Were these truly Martian microbes frozen in time from an ancient wet Mars, or just geological oddities twisted by time and wishful thinking? Skeptics pointed to non-biological processes that could create similar shapes, while supporters highlighted nanomagnetite crystals inside the rock, a mineral some Earth bacteria use like a compass. The controversy still simmers, but newer techniques are tipping the scales. High-resolution microscopes have since revealed organic carbon globules with isotope ratios unlike anything on Earth, and tube-like structures so complex they defy simple mineral explanations. Meanwhile, lab experiments show that certain bacteria, when fossilized in Mars-like conditions, leave behind nearly identical patterns. If LH-84001 does contain fossilized life, it wouldn't just prove Mars once lived, it would suggest life can hop between planets, hitching rides on asteroids blasted free by impact. Panspermia, the idea that life spreads across the cosmos like cosmic pollen, suddenly seems less like science fiction and more like a plausible chapter in our origin story. Imagine a scenario where Mars and Earth traded biological material billions of years ago, swapping microbes in a celestial game of catch. Or consider the possibility that life didn't even start in our solar system, that it arrived here pre-packaged on an interstellar traveler, a gift from some distant star. The implications are dizzying. If life's ingredients are universal and its dispersal as simple as falling rocks, then the galaxy might be a sprawling garden quietly blossoming in the dark. Every meteorite that lands on Earth is a time capsule, a piece of a puzzle we're only starting to assemble. And with missions like Mars Sample return on the horizon, we might soon hold incontrovertible proof that we're not just inhabitants of a living planet, we're citizens of a living universe. LHS 1140b isn't just another exoplanet lost in the cosmic crowd, it's a heavyweight contender in the search for alien life, defying the odds in one of the harshest neighborhoods imaginable. Orbiting a dim red dwarf star 49 light-years away, this super-Earth is nearly 7 times more massive than our home planet, with a density suggesting a rocky core wrapped in a deep, sprawling ocean or a thick, steamy atmosphere. But here's what makes it so tantalizing. Unlike most planets around volatile red dwarfs, LHS 1140b might have clung to its atmosphere despite the relentless radiation blasting from its star. That's like holding onto a snow globe in a hurricane, a feat that could rewrite the rules of where life can survive. Red dwarfs are notorious for their tantrums, frequently erupting with flares powerful enough to strip atmospheres from nearby planets. Yet LHS 1140b's sheer mass might be its saving grace. With gravity almost 3 times stronger than Earth's, any atmosphere it formed in its youth could have resisted being blown away, creating a stable shroud that protects its surface. Even more intriguing, the planet orbits far enough from its star to avoid tidal locking, a rarity for red dwarf worlds, meaning it could rotate like Earth, creating day-night cycles instead of one scorching side and one frozen in darkness. But the real excitement lies in what comes next. The James Webb Space Telescope has this super-Earth in its crosshairs, preparing to analyze starlight filtering through its potential atmosphere. Scientists are hunting for traces of water vapor, carbon dioxide, or even methane gases that could hint at oceans, volcanic activity, or biological processes. If Webb detects nitrogen, that would be a game-changer. It's a stubborn gas that rarely forms without biological or geological recycling, suggesting an active Earth-like world. What if LHS 1140b isn't just a survivor, but a thriving water world? Some models suggest its density points to a global ocean hundreds of miles deep, capped by an ice layer insulated by a dense atmosphere. Imagine the possibilities: hydrothermal vents brewing chemistry in the abyss, or microbial mats floating in the slushy shallows. This isn't just a planet, it's a test case for whether life can endure under the galaxy's harshest spotlights. And with Webb's observations on the horizon, we might soon have our answer, a glimpse into a world that proves life doesn't just need gentle stars, it needs resilience. Tabby's star doesn't behave like any other cosmic object we've ever seen. Officially catalogued as KIC 8462852, this distant sun, lying roughly 1,400 light-years away in the constellation Cygnus, flickers and dims in ways that defy all conventional explanations. When astronomers first noticed its bizarre light patterns in 2015, the data looked almost like a glitch, a star that sometimes plunged in brightness by a staggering 22%, as if something colossal was passing in front of it. But glitches don't repeat, and Tabby's star, it kept doing it. Initial theories pointed to natural causes, maybe a swarm of comets, thousands of them, trailing dust clouds thick enough to blot out a fifth of the star's light. But the math didn't add up. For comets to cause such extreme dips, they'd need to be unrealistically massive, far larger than anything in our own solar system. Even more puzzling, long-term observations revealed the star was gradually dimming over years, as if something was slowly accumulating around it. That's when the whispers began. Could this be evidence of alien engineering on a scale beyond human comprehension? Enter the Dyson sphere hypothesis. Proposed by physicist Freeman Dyson in the 1960s, the idea suggests advanced civilizations might eventually build megastructures around their stars to harness energy. Vast solar collectors, possibly made of orbiting panels or even a solid shell. If such a structure were partially complete around Tabby's star, it could explain both the erratic dimming and the long-term fade. Skeptics, of course, pushed back hard. Dust, not aliens, tends to be the culprit in cosmic mysteries, and in 2018, follow-up studies found evidence that the dimming was wavelength-dependent, meaning smaller particles like interstellar dust were likely scattering the star's light unevenly. Case closed, not quite. New monitoring campaigns have since revealed something even stranger. Some of the star's dips occur with a peculiar symmetry, almost as if designed. While natural dust clouds should scatter light chaotically, Tabby's star's dimming events sometimes follow eerie, repeating patterns. Could there be an artificial structure beneath the dust, something intentionally built, now partially obscured? Or is this just another example of nature outwitting our imaginations? Recent observations with the James Webb Space Telescope aim to settle the debate once and for all, analyzing the star's infrared signatures for heat that would betray artificial constructs. Meanwhile, Tabby's star remains a cosmic Rorschach test. To some, it's a lesson in humility, reminding us how much we still don't understand about the universe. To others, it's a beacon, a flickering signpost that we might not be the only builders in the dark. Whether the answer is dust or something far more extraordinary, one thing's certain: this star refuses to be ignored. Some signals from deep space don't just crackle with cosmic noise, they pulse with eerie, almost artificial precision, like a radio broadcast counting down in perfect rhythm. One of the most baffling examples, the so-called cosmic barcode signals, repeating bursts of energy that arrive with such mathematical regularity. They seem less like natural phenomena and more like deliberate markers. The first of these, detected in 2007, stunned astronomers with its uncanny pattern, a sequence of pulses spaced exactly 17 milliseconds apart, not just once, but over and over, as if tuned by some celestial metronome. At first, researchers assumed they'd stumbled upon a new type of pulsar, the spinning remnants of dead stars known for their clockwork radio emissions. But pulsars slow down over time as they lose energy, their rhythms gradually stretching like an unwinding spring. These barcode signals, they don't drift. They don't waver, they hit the same intervals with precision that defies known physics, as if engineered by something or someone obsessed with perfect timing. Here's where it gets even stranger. Some of these signals, like the one catalogued as FRB 180916, don't just repeat, they cycle through predictable multi-day patterns, flaring up for bursts of activity before going silent for weeks or months. Its behavior more reminiscent of a programmed beacon than a natural cosmic event. Astrophysicists have scrambled for explanations, proposing exotic theories: neutron stars wrapped in supercharged magnetic fields, collisions between ultra-dense objects, or even cosmic strings, hypothetical defects in spacetime left over from the Big Bang. Yet none fully account for the signal's razor-sharp timing or their peculiar on-off cycles. Then there's the frequency. Many of these bursts cluster around 1420 MHz, the same emission line of neutral hydrogen, the most abundant element in the universe. It's a frequency any spacefaring civilization would recognize as a universal landmark, making it an obvious channel for interstellar communication. Could these pulses be navigation buoys scattered across the galaxy to mark routes or resources? or perhaps they're echoes of a long-gone civilization's attempts to signal others, their messages now reduced to cryptic, repeating beats. The truth is, we're still listening. Projects like Breakthrough Listen and the Deep Synoptic Array are scanning the skies for more of these signals, hunting for patterns that might reveal their origins. Every new detection peels back another layer of the mystery, hinting at a universe far more intricate and perhaps far more intentional than we ever imagined. Whether natural or engineered, these cosmic barcodes are a reminder. Deep space hums with rhythms we're only beginning to decode. Mars has been playing a dangerous game of hide and seek with scientists for years, and the stakes couldn't be higher. When NASA Curiosity rover first detected methane wafting through the thin Martian air in 2013, the discovery sent shockwaves through the astrobiology community. Here's why methane matters. On Earth, 95% of atmospheric methane comes from living organisms, from burping cows to thriving microbial communities. So when Curiosity's instruments picked up not just random whiffs but seasonal spikes of the gas, the implications were staggering. Could this be the first whiff of Martian life? The rover's findings revealed something eerily familiar. Methane levels in Gale Crater didn't just fluctuate randomly. They peaked predictably during Mars' late summer months, then dwindled as temperatures dropped. That seasonal rhythm mirrors how methane behaves in Earth's Arctic tundra, where warming soils unleash stored gases produced by microbes. But Mars doesn't have permafrost, at least not the organic, rich kind we know. So what's causing the pattern? Some researchers point to underground reservoirs of methane clathrates, ice-like compounds that trap gas molecules, slowly releasing their contents as the ground warms. Others suggest geological processes like serpentinization, where water reacts with certain rocks to produce methane abiotically. Then came the real curveball. In 2019, Curiosity detected its largest methane spike yet, 21 parts per billion, nearly 3 times the background level. Even more intriguing, the surge vanished within days, as if something or someone had opened a window and let the gas escape. On Earth, such rapid dispersion would imply an active, nearby source. But Mars lacks the atmospheric turbulence to mix gases that quickly, leaving scientists scratching their heads. Some wonder if methane could be seeping from localized vents, perhaps tied to underground aquifers or even ancient, now buried organic material. The plot thickened when Europe's Trace gas orbiter, designed specifically to sniff Martian methane from orbit, repeatedly failed to confirm Curiosity's ground-level detections. This mismatch has sparked a heated debate. Is the rover sitting atop a microscale methane hotspot, or are orbital instruments missing something crucial? New studies suggest methane might break down faster than expected near Mars' surface due to undiscovered chemical reactions, or perhaps it's being consumed by hypothetical surface bacteria, a haunting echo of how terrestrial microbes metabolize the gas. There's another spine-tingling possibility. On Earth, certain methane-producing microbes thrive in extreme environments like deep underground or inside volcanic rocks without needing oxygen or sunlight. If similar organisms exist beneath Mars' radiation-blasted surface, their seasonal releases could explain the data. Future missions like NASA Mars Life Explorer aim to drill deeper than ever before, hunting for subsurface biosignatures. Imagine if they hit pay dirt microbes exhaling methane in the dark, a subterranean biosphere we never knew existed. Until then, every whiff of Martian methane teases us with the same electrifying question: are we alone or just late to the party? The universe just handed us a whole new category of worlds where life might be hiding in plain sight: Hycean planets. Picture this: a planet larger than Earth but smaller than Neptune, wrapped in a thick, steamy atmosphere of hydrogen, with surface temperatures hot enough to keep water liquid but not so extreme that life couldn't take root. Beneath those hazy skies, a planet-wide ocean deeper than anything on Earth, sloshing beneath an eternal twilight. these aren't just theoretical curiosities. Astronomers have already pinpointed real candidates, and they might be the most promising places we've ever found to search for alien biology. What makes Hycean planets so special starts with their chemistry. Unlike Earth's nitrogen and oxygen air, their atmospheres are dominated by hydrogen, a gas so light it usually floats away into space. But on these worlds, gravity holds it in place, creating a dense, pressurized blanket that traps heat and could shield life from cosmic radiation. While that hydrogen-rich air would be toxic to humans, certain extremophiles on Earth thrive in similarly harsh conditions, like the microbes lurking in hydrothermal vents or buried deep in oil reservoirs. If life can survive there, why not in the soupy depths of a Hycean ocean? Then there's the water. These planets are thought to be drenched in it, not just in patches, but as global seas hundreds of miles deep. With no land in sight, their ecosystems could resemble Earth's early oceans, where chemistry bubbled unchecked for eons before life emerged. The intense pressure at those depths might even create exotic forms of ice like superionic water, a bizarre state where water molecules break apart, forming a lattice of oxygen atoms swimming in a sea of hydrogen ions. It's the kind of environment that sounds inhospitable, but nature has a habit of surprising us. The real excitement lies in how easy these planets might be to study. Hydrogen atmospheres are transparent to infrared light, meaning telescopes like the James Webb can peer straight through them to analyze the chemistry of their oceans. Scientists are already hunting for biosignatures like methyl chloride or dimethyl sulfide gases that, on Earth, are almost exclusively produced by living organisms. One prime candidate, K218b, made headlines when Webb detected potential traces of dimethyl sulfide in its atmosphere. If confirmed, it could mean microbial life is not just possible on Hycean worlds, it might already be there, exhaling its presence into the cosmos. But here's the twist: life on a Hycean planet wouldn't look anything like Earth's. With no sunlight penetrating those thick clouds, organisms might rely on chemical energy from hydrothermal vents, or even harness the hydrogen-rich atmosphere itself for metabolism. Some scientists speculate they could form vast, floating mats in the upper ocean, like a planetary-scale version of Earth's primordial soup. Others imagine creatures adapted to crushing pressures, their biology built around stable molecules we can't yet conceive. Hycean planets force us to rethink the very definition of habitable. They're not Earth twins, they're something wilder, something alien, and that's what makes them so thrilling. If life can thrive in these pressure cooker worlds, then the galaxy might be teeming with biospheres we've only just begun to imagine. The hunt for Hycean planets isn't just about finding life. It's about discovering how inventive life can be when given a canvas as vast as the cosmos. Ceres, the largest object in the asteroid belt, was once written off as a barren, frozen relic of the solar system's birth, until the Dawn spacecraft peeled back its secrets to reveal something astonishing. In 2017, Dawn's infrared spectrometer spotted dark patches of material rich in aliphatic organic compounds near the dwarf planet's Ernutet crater. These weren't just simple carbon molecules, they were complex chains, the kind that on Earth serve as building blocks for fats, cell membranes, even crude oil. The discovery sent shockwaves through the astrobiology community because Ceres shouldn't have these materials. Not here, not in such abundance. What makes these organics so baffling is their location. They're not scattered evenly across Ceres' surface but concentrated in peculiar splotches, as if something pushed them up from below. That something might be even more intriguing than the molecules themselves: subsurface brines, salty liquid reservoirs lurking just beneath the crust. Ceres has long hinted at hidden waters, with Dawn spotting mysterious bright spots in Ocata crater later confirmed to be sodium carbonate deposits, essentially salt left behind by evaporating brine. If those brines are still active today, oozing upward through cracks in the ice, they could be delivering fresh organics to the surface like a cosmic conveyor belt. Theories abound about where these compounds originated. Some scientists argue they formed right on Ceres, cooked up in hydrothermal systems where water, heat, and minerals reacted over billions of years. Others propose they arrived via carbon-rich asteroids that battered Ceres in its youth, their organic payloads preserved in the dwarf planet's icy shell. But here's the twist. Dawn's data suggests these organics are too concentrated to be asteroid debris. Their distribution points to an internal source, perhaps even ongoing chemistry in Ceres' briny depths. Imagine what that could mean. On Earth, hydrothermal vents are thriving hubs of life, their mineral-rich fluids fueling entire ecosystems cut off from sunlight. If Ceres has similar environments, pockets of warm brine swirling beneath its surface, they could be mixing simple organics into ever more complex chains. No one's suggesting there are microbes swimming in Ceres' underground seas, but the mere possibility that probiotic chemistry is still active there rewrites the narrative of where life's ingredients can assemble. The implications stretch far beyond our solar system. If a small, icy world like Ceres can brew and concentrate organics, then countless similar bodies orbiting other stars might be doing the same. Suddenly, the building blocks of life aren't rare treasures, they're cosmic commonplace, simmering in the dark on dwarf planets and moons we've barely begun to explore. Future missions could drill into Ceres' crust, tasting its brines for even more complex molecules. Until then, this tiny world stands as a reminder. Sometimes the most promising places to search for life's origins aren't planets at all, but the small, icy wanderers hiding in plain sight. What if the clearest sign of alien life isn't biology at all, but the glow of their city lights, the smog of their industry, or even the heat signatures of colossal megastructures? The search for extraterrestrial intelligence has entered a radical new phase, hunting not for radio signals or microbes, but for technosignatures, the unmistakable fingerprints of technology imprinted on the cosmos. And with next-generation telescopes now capable of sniffing out atmospheric pollution on distant worlds, or spotting artificial illumination flickering on an exoplanet's night side, we're closer than ever to detecting a civilization that might not even know we're watching. Take the hunt for alien megacities. On Earth, urban centers blaze with light after sunset, creating a distinct glow visible from space. Now, astronomers are training telescopes like NASA James Webb to scan the terminator lines of exoplanets, the twilight border between day and night, for similar unnatural radiance. A planet tidally locked to its star, with one side perpetually dark, might reveal clusters of artificial lights concentrated in specific regions, like Vegas-style oases in an otherwise blackened landscape. Even more telling, the light spectrum. Sodium vapor streetlights or LED grids would leave sharp, unnatural spikes in the data, screaming, designed in a universe that favors smooth thermal curves. Then there's atmospheric forensics. Just as human industry laces Earth's air with chlorofluorocarbons and nitrogen dioxide, an advanced alien society might inadvertently fill their skies with industrial byproducts. The James Webb Telescope has already proven it can detect complex molecules in exoplanet atmospheres. Imagine if it spotted tetrafluoromethane, a greenhouse gas thousands of times more potent than CO2, which on Earth exists only as a byproduct of aluminum production. Or what about chloroform, a compound so unstable it requires constant replenishment? Finding either would suggest something or someone is actively maintaining their presence. But the most tantalizing technosignatures might be the ones we can't yet imagine. Consider Dyson Swarm's hypothetical energy harvesting structures encircling stars to capture their power. While a complete Dyson sphere would block a star's light entirely, partial installations would emit waste heat in the mid-infrared range, appearing as anomalous warm spots against the cold backdrop of space. Projects like the Gaia spacecraft are already scanning millions of stars for such infrared outliers, And while most turn out to be dust-shrouded stars or young planetary systems, a handful defy explanation. One candidate, TIC 6111-1162-1, flickers erratically while blasting excess infrared, behavior that mirrors what theorists predict for a partially built Dyson swarm. Of course, the universe loves to mimic technology with natural phenomena. Pulsars were initially mistaken for alien beacons, and interstellar asteroids like Oumuamua sparked wild speculation before settling into the realm of cosmic oddities. But the difference now is precision. Upcoming observatories like the Habitable Worlds Observatory and the Square Kilometre Array will dissect exoplanet atmospheres with unprecedented resolution, while AI-driven algorithms sift through petabytes of data for patterns no human could spot. This isn't just about finding aliens, it's about recognizing that intelligence, if it exists out there, might announce itself not through deliberate messages, but through the unavoidable side effects of its ambition. A civilization advanced enough to reshape its world inevitably leaves traces, whether it intends to or not. And as our tools grow sharper, we're learning to read those traces like cosmic tea leaves, searching for the faintest glimmer of a hand that isn't human. The universe might be silent, but it's far from empty, and the things we're listening for now aren't voices, but echoes of machines, cities, and the quiet hum of someone else's everyday life. Pulsars are nature's most precise timekeepers, spinning neutron stars that flash beams of radiation with metronomic regularity, some keeping rhythms more accurate than Earth's atomic clocks. But in 2012, astronomers stumbled upon a pattern so peculiar it defied the odds. A cluster of pulsars arranged in precise geometric alignment, their beams sweeping across the cosmos like synchronized galactic lighthouses. The probability of this happening by chance statistically negligible. It's as if someone arranged them deliberately, a network of celestial beacons lighting up the void. The most famous example lies in the constellation Sagittarius, where a group of millisecond pulsars, some spinning hundreds of times per second, form a near-perfect three-dimensional grid. Their rotational axes all point toward the same patch of sky, a region centered on the supermassive black hole at the Milky Way's core. Coincidence unlikely. Natural processes don't typically orchestrate such symmetry across light years of space. The arrangement has fueled speculation that these pulsars might serve a purpose beyond astrophysics, perhaps as navigation markers for civilizations traversing the galaxy. Here's what makes the idea tantalizing. Pulsars emit unique signature pulses like cosmic fingerprints. Any spacefaring species could use these predictable signals as triangulation points, plotting courses between stars the way ancient mariners relied on constellations. Even more intriguing, millisecond pulsars, the ones in these aligned clusters, are exceptionally stable, their rhythms barely drifting over millennia. They're the perfect natural GPS. Some researchers have theorized that if a civilization wanted to leave a lasting, universal roadmap, engineering pulsars into alignment wouldn't be beyond the realm of possibility. After all, advanced beings might harness the energy of neutron stars, tweaking their spins or orientations as needed. Of course, skepticism abounds. Astrophysicists point to rare but plausible natural explanations, like pulsars born from the same stellar cluster inheriting aligned spins, or gravitational interactions with the galactic center nudging them into symmetry over eons. Yet even these theories struggle to explain the sheer precision of the alignments observed. The odds remain astronomically low, like rolling a dozen dice and having each land on the same number consecutively. The implications are dizzying. If these pulsars were deliberately arranged, whoever or whatever did it would need technology capable of manipulating stellar remnants, a feat that borders on godlike. It raises questions we're only beginning to grapple with. Would a civilization advanced enough to engineer pulsars even need physical markers, or might they leave them as a legacy, a way to guide others? And if this is a signal, how many more are hidden in plain sight, waiting for us to decode them? Future radio telescopes, like the Square Kilometre Array, will map pulsar alignments with unprecedented precision, hunting for patterns that defy randomness. Until then, these cosmic lighthouses stand as silent sentinels, their synchronized flashes either a fluke of nature or the closest thing we've found to a welcome sign etched in the stars. One thing's certain, the galaxy just got a lot more mysterious. Venus has long been dismissed as a geological graveyard, a planet so choked by its own violent history that its surface froze in time billions of years ago. But new radar images are shattering that assumption, revealing a world that might still be stirring beneath its toxic clouds. In 2023, researchers analyzing data from NASA's Magellan spacecraft spotted something impossible to ignore. Fresh lava flows near Venus's Mons, a towering volcano that rivals Earth's Mount Everest. These weren't ancient relics of some bygone era. The flows showed crisp, uneroded edges and distinct thermal signatures, hallmarks of eruptions that might have occurred within the past few decades, maybe even last year. What makes this so groundbreaking isn't just the discovery of active volcanism. It's what it means for the search for life. On Earth, we've found entire ecosystems thriving in the scalding vents of underwater volcanoes, where heat and minerals create oases in the abyss. If Venus is still geologically alive, its subsurface could harbor similar pockets of habitability, regions where temperatures and pressures drop just enough for liquid water to exist, shielded from the 700-degree furnace at the surface. Imagine extremophile microbes clinging to volcanic fissures, sustained by chemical reactions between rock and trace moisture, or entire biospheres huddled in lava tubes insulated from the crushing atmosphere outside. The evidence keeps mounting. In 2022, scientists identified coronae, crown-like geological features formed by plumes of hot rock rising from Venus's mantle that appear freshly deformed, as if reshaped by recent activity. Some even emit higher than expected temperatures, hinting at molten rock close to the surface. Then there's the strange transient hotspots detected by Europe's Venus Express orbiter, localized spikes in infrared radiation that vanished within days, like geological flashbulbs popping off in the dark. Skeptics argue these could all be flukes, residual heat from old eruptions, or instrument artifacts. But here's the clincher: Venus's atmosphere contains abnormally high levels of sulfur dioxide, a gas typically belched out by volcanoes. The concentrations fluctuate wildly, as if something below is periodically replenishing the supply. Combined with the radar data, it paints a picture of a world that isn't just sporadically coughing up lava, but potentially maintaining a slow, steady churn of geothermal activity. Future missions like NASA Veritas and Europe's Envision aim to settle the debate, mapping Venus's surface in unprecedented detail to catch volcanoes in the act. If they succeed, we might have to stop thinking of Venus as Earth's dead twin and start seeing it as a world with secrets still simmering beneath its hellish facade. The discovery wouldn't just rewrite planetary science, it would force us to confront a tantalizing possibility: life might not need a Goldilocks planet to survive. Sometimes all it needs is a crack in the door. Imagine a planet torn from its star, hurled into the endless dark between galaxies, no sunlight, no warmth, just an endless drift through the freezing void. It sounds like a death sentence for any chance of life, but nature always finds a way. Some of these rogue planets, flung from their solar systems by gravitational chaos, might carry a secret beneath their icy shells, vast hidden oceans kept liquid by the slow, steady heat of radioactive decay. These aren't just frozen wastelands, they could be cosmic arcs carrying the ingredients for life through the interstellar abyss. The concept hinges on a simple but radical idea: that a planet doesn't need a star to be habitable. Earth's heat comes mostly from the sun, but deep underground radioactive elements like uranium, thorium, and potassium-40 constantly break down, generating warmth. On a rogue planet, especially one with a thick insulating layer of ice, this natural furnace could maintain subsurface oceans for billions of years. In fact, calculations suggest some of these worlds might stay warmer than Europa or Enceladus, with liquid layers dozens of miles deep. That's more than enough volume to host ecosystems entirely cut off from the universe above. But how would life even get started in such a place? The answer might lie in hydrothermal vents. On Earth, these underwater geysers act as biological incubators, where heat and minerals fuel chemosynthetic microbes at the base of complex food webs. A rogue planet's ocean, churned by tidal forces from a massive moon or residual planetary motion, could develop similar hotspots. Radioactive decay would provide the energy, while minerals leaching from the rocky core would supply raw materials. Over eons, simple chemistry could give rise to something far more complex. The most mind-bending part, these planets might outnumber stars in the Milky Way. Current estimates suggest there could be billions of rogue worlds drifting unseen through our galaxy, far beyond the glow of any sun. Some may have been ejected during their system's violent early days, while others could be failed stars, objects nearly large enough to ignite fusion but left to wander instead. If even a fraction of them host subsurface oceans, the galaxy's habitable real estate just exploded. Detecting these hidden biospheres is another challenge entirely. Traditional methods like transit photometry, which spots planets as they pass in front of their stars, won't work here, but astronomers have proposed hunting for rogue planets through gravitational microlensing, where their mass bends light from distant stars as they drift by. Future telescopes might even catch infrared glimmers from geothermal heat seeping through cracks in the ice, and if we ever find proof of life on one, it would shatter every assumption about where biology can take root. A rogue planet's inhabitants wouldn't just survive without sunlight, they'd never know it existed. Their entire universe would be the dark, pressurized depths of their buried ocean, a realm where life flourishes not in spite of isolation, but because of it. These wandering worlds might be the ultimate survivors, carrying the flame of life through the coldest, loneliest stretches of the cosmos. If that's true, then the galaxy isn't just dotted with life, it's teeming with it, floating silently in the dark, waiting to be found. Kepler 1649c isn't just another exoplanet lost in the cosmic sea. It's the closest match to Earth we've ever found outside our solar system. Discovered in 2020 after a painstaking reanalysis of old Kepler Space Telescope data, this world sits just 300 light-years away, orbiting a dim red dwarf star in the constellation Cygnus. At first glance, the numbers alone make your heart race. 1.06 times Earth's size, with a surface temperature that, given the right atmosphere, could allow liquid water to pool. But here's what truly sets it apart. It receives 75% of the stellar energy Earth gets from the Sun, placing it squarely in its star's habitable zone. That's a Goldilocks balance we've rarely seen, even among the thousands of exoplanets catalogued so far. What makes Kepler 1649c so tantalizing isn't just its Earth-like stats, it's the eerie familiarity of its orbit. This planet circles its star every 19.5 Earth days, a blistering pace compared to our leisurely year. But because its star is smaller and cooler than the Sun, that tight orbit still keeps it comfortably within the sweet spot for liquid water. Even more intriguing, it shares its system with at least one other planet, Kepler 1649b, a rocky neighbor orbiting closer in. Their gravitational dance is so finely tuned that their orbits resonate in a perfect 4:3 ratio, meaning for every 4 laps the inner planet completes, Kepler 1649c finishes exactly 3. This kind of harmony is rare, hinting at a system that's avoided catastrophic collisions and maintained stability for eons. The real magic, though, lies in the unanswered questions. Does Kepler 1649c have an atmosphere? If so, is it thick with nitrogen and oxygen like Earth's, or a suffocating blanket of carbon dioxide like Venus? Red dwarfs are notorious for their violent youth, often stripping atmospheres from nearby worlds with relentless flares. Yet this planet star, Kepler 1649, is unusually calm for its kind, a quiet elder statesman with far fewer eruptions than its peers. That stability might have given the planet a fighting chance to hold onto its air, or even develop one over time through volcanic outgassing. Then there's the wild card of tidal locking. Most planets orbiting red dwarfs are thought to turn one face permanently toward their star, creating a scorching day side and a frigid night side. But simulations suggest Kepler 1649c could be an exception. Its slightly eccentric orbit might induce a slow rotation, creating a day-night cycle not unlike Earth's, a rare gift in a red dwarf system. That could mean more temperate conditions across its surface, with weather patterns distributing heat instead of leaving one hemisphere baked and the other frozen. The James Webb Space Telescope could soon deliver answers. While Kepler 1649c's small size makes atmospheric studies challenging, its star's dimness actually works in our favor. Starlight filtering through any atmosphere would stand out like a beacon. If Webb detects water vapor, methane, or even oxygen, it would transform this world from a statistical twin into a potential biological sibling. Until then, Kepler 1649c remains a glittering possibility, a reminder that Earth might not be one of a kind, but one of many. And if life could take hold here under the ruby glow of a quiet red sun, then the universe might be far more hospitable than we ever dared to dream. Deep in the cosmic web, where galaxies should cluster like fireflies in the night, there are voids so vast and empty they defy logic. These are the cosmic empty zones, regions spanning billions of light years where telescopes find nothing but chilling darkness. No stars, no galaxies, just an unsettling nothingness stretching farther than our minds can grasp. But here's the twist: these voids might not be empty at all. They could be hiding something, or someone deliberately staying out of sight. Take the Boötes Void, for example. Discovered in the 1980s, this spherical abyss is 330 million light-years wide. If you drop the Milky Way into its center, the next galaxy would be so far away, our night sky would appear almost entirely black. Statistically, this void should contain at least 2,000 galaxies. Yet fewer than 60 have been found. Where did everything go? Some astrophysicists argue these voids are natural expanding bubbles left behind by ancient gravitational tugs during the universe's infancy. But others whisper a more radical idea. What if advanced civilizations learn to cloak their galaxies, rendering them invisible to our telescopes? The concept isn't as far-fetched as it sounds. A Type 3 civilization on the Kardashev scale, one capable of harnessing the energy of an entire galaxy, might dismantle stars to build megastructures like Dyson spheres, absorbing their light and leaving no trace. Or perhaps they've mastered spacetime itself, warping light around their worlds like a cosmic invisibility cloak. If such beings exist, the emptiest parts of the universe would be the perfect place to hide, far from the chaos of colliding galaxies or prying eyes. Then there's the eerie case of dark galaxies, massive collections of matter that emit almost no light. Some voids emit faint radio waves or gravitational lensing effects, hinting at unseen mass lurking in the dark. Could these be the footprints of civilizations that converted their stars into computational networks, trading visible energy for processing power? Or maybe they've engineered their environments to minimize entropy, slowing time itself to preserve their existence across eons. The most provocative theory comes from cosmologist Andre Lind, who suggests these voids might not be accidents, but intentional reset zones, regions where a prior universe collapsed and rebooted, leaving behind pockets of nothingness like cosmic scars. If true, the emptiness isn't a void at all, but a relic of something older than time. For now, the mystery endures. Upcoming telescopes like the Vera Rubin Observatory will map these voids in unprecedented detail, hunting for gravitational whispers or thermal anomalies. Until then, these silent stretches of space remain the universe's greatest riddle. Are they the aftermath of ancient physics, or the deliberate work of intelligence beyond our comprehension? One thing's certain: the darkest corners of the cosmos might be hiding the brightest secrets. Europa's icy shell has always been a tantalizing veil, hiding what might be the solar system's most promising ocean. But cracks in that frozen facade are starting to reveal something astonishing: not just water, but the very building blocks of life itself. In 2024, the James Webb Space Telescope delivered a bombshell: patches of carbon-rich compounds scattered across Europa's surface, concentrated near its infamous chaos terrains, jumbled regions where the ice has fractured and refrozen in chaotic patterns. These aren't just random stains, they're chemical fingerprints, and their arrangement suggests they didn't come from comet impacts or interstellar dust. They bubbled up from below. The key to this discovery lies in Europa's plumes. When Hubble first spotted watery geysers erupting from the Moon's south pole, scientists speculated they were venting material from the subsurface ocean into space. Webb's infrared eyes confirmed it, detecting organic molecules like carbon dioxide and ethane mixed with the plume material compounds that, on Earth, often signal biological activity. But the real surprise came when researchers mapped their distribution. The organics weren't evenly dispersed. They clustered along fracture lines and around areas where plume activity has been most intense, like discarded crumbs leading back to a hidden feast. What makes these compounds so exciting is their complexity. Simple organics like methane can form abiotically, but the molecules Webb detected include heavier, more elaborate chains, the kind that typically require energy and time to assemble. On Earth, similar compounds form near hydrothermal vents, where heat and minerals catalyze chemical reactions that build ever more complex structures. If Europa's ocean hosts similar environments, its plumes could be delivering not just water, but probiotic ingredients, maybe even the precursors to life itself, straight to the surface. Then there's the eerie coincidence of location. The densest organic deposits overlap with regions where NASA Europa Clipper mission, launching later this year, plans to conduct low-altitude flybys. This isn't just luck, it's a calculated bet that these areas are Europa's most chemically active, and therefore most likely to offer clues about what's happening in the ocean below. Clipper's instruments will analyze plume material in real time, hunting for amino acids or lipids, molecules that would push the needle from interesting chemistry toward potential biology. Skeptics caution that organics alone don't equal life. Europa's compounds could be the result of purely geological processes like serpentinization, a reaction between water and rock that produces hydrogen and simple hydrocarbons. But even that would be groundbreaking. Serpentinization fuels ecosystems on Earth, providing energy for microbes in places like the Lost City hydrothermal field. If Europa's ocean is churning out organics through similar reactions, it could be setting the stage for life even without sunlight or oxygen. The implications stretch far beyond one icy moon. If Europa's plumes are indeed ferrying organics from ocean to surface, they're offering us a free sample of what might lurk in the dark. Future missions could land near these deposits, scooping up material that fell from the depths without ever needing to drill through miles of ice. It's like the moon is handing us a menu, and every dish listed hints at a hidden world more vibrant than we ever imagined. The more we learn, the clearer it becomes. Europa isn't just a frozen ball. It's a chemist's workshop, a potential nursery, and maybe, just maybe, a beacon in the search for life beyond Earth. When hunting for signs of extraterrestrial intelligence, you don't just point a telescope at random stars and hope for the best. You follow the clues, and right now, the most promising lead is a meticulously curated catalog of exoplanet systems that have already shown hints of being habitable. In 2022, researchers from the SETI Institute and NASA teamed up to compile the ultimate cosmic cheat sheet, a ranked list of star systems where technosignatures, artificial signals or structures are most likely to be detected. This isn't guesswork. Each target was selected because it ticks two critical boxes. First, it hosts planets confirmed to transit or pass in front of their star from our vantage point, a geometry that allows us to study their atmospheres. Second, those worlds sit in the habitable zone with conditions that could allow liquid water. Take the system known as TOI 700, for example. This dim red dwarf star, located just over 100 light-years away, made the catalog's top tier because it hosts a rare gem TOI 700d, an Earth-sized planet soaking up 86% of the stellar energy Earth receives from the Sun. But here's what makes it a SETI goldmine. The planet is tidally locked, meaning one side basks in permanent daylight while the other freezes in eternal darkness. That might sound inhospitable, but the twilight strip along the Terminator line could offer temperate conditions perfect for life. More importantly, a civilization on such a world might rely on technology to redistribute heat or energy across its surface infrastructure that could leak detectable signals, like concentrated radio transmissions or even waste heat patterns visible in infrared. Then there's the L9859 system, another priority target. This one boasts a super-Earth, L9859b, orbiting squarely in the habitable zone of its calm, sun-like star. What sets it apart is the planet's potential for a thick atmosphere critical for sustaining life, but also for amplifying any artificial signals. On Earth, our atmosphere acts like a mirror for certain radio frequencies, bouncing them back to the surface and preventing them from escaping into space. If L9859b has a similar layer, any civilization there might unintentionally create a planetary-scale radio lighthouse, beaming amplified signals into the cosmos whenever they use high-power communications. SETI Allen Telescope Array has already spent hundreds of hours listening to this system, scanning for narrowband radio pulses, the kind natural sources almost never produce. But the catalog's real genius lies in its strategic diversity. Not all targets are Earth twins. Some, like the TRAPPIST-1 system, offer a buffet of rocky worlds packed close together, increasing the odds that if one planet develops intelligence, its neighbors might too. Others, like Kepler 442b, orbit stars so stable they've likely provided billions of extra years for life to evolve advanced technology. And a handful of targets, like JWST, were chosen simply because they're nearby, close enough that if we did detect a signal, we might actually be able to send a reply within a human lifetime. This isn't just a list of coordinates, it's a roadmap for the next decade of SETI research, shaped by breakthroughs in exoplanet science and radio astronomy. With new telescopes like the Square Kilometre Array coming online, capable of detecting airport radar-level transmissions from dozens of light-years away, the catalogue ensures we're searching where the cosmic whispers are most likely to be heard. The universe is vast, but for the first time, we're not just listening blindly, we're leaning in, tuning our ears to the frequencies of worlds that have already raised their hands and said, "Here we are." Now all we have to do is catch them speaking. Mars has long been thought of as a frozen desert, a world where water exists only as ice or vapor, locked away in polar caps or thin wisps of atmosphere. But in 2018, the European Space Agency's Mars Express orbiter cracked open that assumption with a revelation straight out of science fiction. A vast, shimmering lake of liquid water, hidden beneath a mile of ice at the planet's south pole. This wasn't just a damp patch or a trickle. Radar scans revealed a body of water spanning 12 miles across, buried under layers of frozen carbon dioxide and dust, a subglacial oasis in the most inhospitable place imaginable. The discovery hinged on a technique familiar to Earth's polar scientists, radar sounding. Just as ice-penetrating radar unveils hidden lakes beneath Antarctica, the MARSIS instrument aboard Mars Express sent radio pulses through the red planet's icy crust, measuring how they bounced back. When the signals hit something highly reflective, like liquid water, they returned with a brightness that couldn't be explained by rock or ice alone. But how could liquid water survive in such frigid conditions? The answer lies in a briny cocktail of dissolved salts, likely perchlorates, the same compounds that keep water liquid in Mars' recurring slope lineae. Mixed into the water, these salts act like antifreeze, depressing its freezing point to as low as -90 degrees Fahrenheit. Add in the crushing pressure from the overlying ice, and you've got a recipe for a stable, albeit alien, aquatic environment. But the surprises didn't stop there. Follow-up studies in 2020 uncovered not just one, but multiple smaller lakes clustered around the main reservoir, like satellites orbiting a central hub. These pockets are scattered across an area larger than Germany, suggesting a network of hidden waterways beneath Mars' desolate surface. Some researchers speculate these lakes could be interconnected, forming a subterranean hydrological system akin to Earth's subglacial lakes in Antarctica. If true, it's possible these waters have been in contact with Mars' rocky crust for eons, leaching minerals and possibly even harboring geothermal hotspots, places where microbial life, if it exists, could find both energy and nutrients. The implications are staggering. On Earth, subglacial lakes like Antarctica's Lake Vostok are teeming with extremophiles, organisms adapted to total darkness, extreme cold, and crushing pressure. These microbes survive by metabolizing minerals in the water or organic material trapped in the ice, forming entire ecosystems cut off from the sun for millions of years. If similar life took root on Mars before the planet dried up, these briny lakes could be its last refuge, a sanctuary sealed away from the radiation and thin air above. Yet not everyone's convinced. Some scientists argue the radar signals could be explained by layers of clay or conductive minerals, which can mimic the reflective properties of liquid water. Others point out that without direct sampling, we can't rule out exotic, non-aqueous explanations. But in 2021, a team of researchers reanalyzed the data with a new algorithm, ruling out most alternative hypotheses. Their conclusion: liquid water is the simplest, most plausible answer. The next step, touching the water itself. Proposed missions like NASA Icebreaker or Europe's Mars Exploration Ice Mapper aim to drill through the polar ice, searching for microbial DNA or metabolic byproducts. Imagine if they strike liquid, not just confirming the lakes, but tasting their chemistry for the first time. It would be a discovery on par with finding life on Europa's ocean, proof that even in the solar system's harshest corners, water finds a way. And where there's water, there's always the whisper of life. While Mars and Europa dominate headlines in our solar system, the transiting Exoplanet survey satellite TESS has been quietly rewriting the playbook on where life might thrive beyond our cosmic neighborhood. Since its launch in 2018, this unassuming telescope has scanned over 85% of the sky, uncovering thousands of exoplanet candidates. But the real treasures are the handful that orbit in their stars' habitable zones, regions where temperatures could allow liquid water. At the top of that list sits TOI 700d, a world that ticks more boxes for potential habitability than almost any other discovery in recent memory. TOI 700d isn't just another exoplanet. It's a rocky world only slightly larger than Earth, orbiting a calm, cool red dwarf star 100 light-years away. What sets it apart is its orbit, 37 days long, placing it squarely in the star's habitable zone with just enough stellar energy to keep water liquid without boiling it away. But here's the kicker: unlike most planets around red dwarfs, which are prone to violent flares that strip atmospheres, TOI 700 is remarkably stable. Observations show no significant flare activity, meaning this planet might have held onto its atmosphere and any potential biosphere for billions of years. Then there's the climate. Early modeling suggests TOI 700d could be tidally locked, with one side perpetually facing its star and the other shrouded in darkness. But instead of creating a scorching dayside and frozen nightside, global winds might redistribute heat across the planet, creating a narrow temperate band along the twilight edge where conditions could be just right for life. Imagine a world where the sun never rises or sets, but hangs eternally at the horizon, casting long shadows over alien forests or vast microbial mats adapted to perpetual dusk. TOI 700d isn't alone. TESS has unveiled a growing catalogue of habitable zone worlds, each with its own quirks. Take TOI 451b, a rare planet orbiting a young, sun-like star, offering a glimpse into what Earth might have looked like in its infancy. Or TOI 1266b, a super-Earth with a proposed water-rich atmosphere, where the sheer humidity could create a global greenhouse effect, trapping heat even at the outer edge of the habitable zone. These aren't just data points, they're windows into the staggering diversity of environments where life might find a way. The real power of TESS lies in its strategy. Unlike Kepler, which stared at a single patch of sky, TESS conducts a near-all-sky survey, catching planets around brighter, closer stars, making them prime targets for follow-up studies. The James Webb Space Telescope has already begun scrutinizing TOI 700d's atmosphere, hunting for traces of water vapor, carbon dioxide, or even methane. A whiff of oxygen would be the ultimate jackpot, as it's a gas that rarely lingers without biological or geological replenishment. With every new TESS discovery, the cosmic map of potential life grows richer. These worlds aren't just scientific curiosities, they're test cases for the resilience of biology in a universe that seems determined to surprise us. Whether it's a tidally locked world like TOI 700d or a steamy super-Earth like TOI 1266b, each one pushes the boundaries of where we dare to imagine life could thrive. And with TESS still scanning the skies, the next groundbreaking discovery might already be hiding in the data, waiting for us to connect the dots. Deep in the frigid emptiness between stars, where temperatures plunge hundreds of degrees below zero and darkness reigns, something extraordinary is brewing, a molecular soup so rich in life's ingredients, it could rewrite our understanding of how biology takes root in the cosmos. Astronomers peering into these interstellar nurseries have found more than just simple gases. They've uncovered sprawling clouds laced with ribose, glycine, and even ethanol, molecules that form the backbone of DNA, proteins, and cell membranes. These aren't random chemicals, they're the exact blueprints life uses to assemble itself, floating freely in space long before planets even form. Take the Sagittarius B2 molecular cloud, a sprawling stellar nursery 25,000 light-years away. Radio telescopes probing its depths have detected over 50 different organic compounds, from formaldehyde to the sugary molecule glycolaldehyde. On Earth, glycolaldehyde is a key player in the formation of RNA, the molecule many scientists believe was life's first genetic material. Finding it in space suggests the universe might be pre-loaded with life's instruction manual, scattering these critical ingredients wherever stars and planets are born. The real shocker came when researchers spotted amino acids, the Lego blocks of proteins, in meteorites and cometary material. The Murchison meteorite, which fell to Earth in 1969, contained over 70 different amino acids, including many not found naturally on our planet. But how did these complex molecules survive the violent chaos of planet formation? The answer lies in ice. Interstellar ices coating dust grains act as cosmic chemistry labs, shielding fragile organics from radiation while providing a surface for atoms to link up into ever more complex structures. When warmed by starlight or shock waves, these ices undergo reactions that can produce everything from sugars to nucleobases, the very letters of life's genetic code. Here's where it gets even wilder. In 2022, the James Webb Space Telescope identified ethanol and acetic acid in a protoplanetary disk around the young star Iris 46. These molecules weren't just floating idly, They were concentrated in regions where future planets might coalesce, like cosmic spice racks stocked for the moment life starts cooking. The implications are staggering. Instead of life's ingredients forming painstakingly on planets over eons, they might arrive pre-packaged, delivered by comets and asteroids to embryonic worlds. But the most tantalizing clue comes from chirality, the handedness of molecules. On Earth, life overwhelmingly uses left-handed amino acids and right-handed sugars, a preference long thought to be accidental. Yet in 2016, researchers found a slight excess of left-handed amino acids in the meteorites that fell over Antarctica. If this asymmetry originated in space, it could mean the universe has a subtle bias toward the chemistry life needs, a nudge written into the fabric of reality itself. What does all this mean for the search for life? It suggests biology might not be a rare accident, but an inevitability waiting for the right conditions. From the icy clouds between stars to the meteorites crashing onto young planets, the cosmos seems obsessed with building the pieces of life long before cells ever form. The universe isn't just hospitable to life, it's practically insistent on it, weaving life's components into the very dust of creation. And if that's true, then every star we see might be lighting the way to another experiment in biology, another chapter in a story that began not on Earth, but in the cold, fertile dark between the stars. 30 cosmic discoveries, each one a thread in the grand tapestry of possibility, each whispering the same tantalizing truth: we are almost certainly not alone. From the salt-streaked plumes of Europa to the methane mysteries of Mars, from the organic-laced clouds of Venus to the deep-oceaned abyss of Enceladus, the evidence isn't just piling up, it's converging. These aren't isolated curiosities, they're pieces of a puzzle so vast it rewrites our place in the universe. Life isn't some fluke confined to Earth's Goldilocks comfort. It's a fighter thriving in acid clouds, buried under ice sheets, even dancing in the toxic rivers of distant Hycean worlds. And if life can blossom in such hostile corners of our own solar system, imagine what wonders might lurk among the trillions of planets beyond. Consider the patterns. Water, not just frozen or vapor, but liquid, keeps bubbling up where we least expect it. Chemistry we once thought unique to Earth, amino acids in meteorites, complex organics on Ceres, turns out to be cosmic graffiti, scrawled across asteroids, moons, and the void between stars. Even the laws of physics seem to tilt in life's favor, with molecules in space mirroring the same chiral preferences found in our DNA. And then there are the anomalies, the wow. Signals uncanny frequency, the pulsars aligned like galactic lighthouses, the exoplanet atmospheres laced with gases that on Earth mean industry or biology. The universe isn't just hinting that life exists elsewhere, it's practically shouting, but the most thrilling chapter is still being written. In mere months, NASA Europa Clipper will skim the icy plumes of Jupiter's moon, tasting their chemistry for signs of amino acids or lipids, molecules that could confirm an ocean not just habitable but inhabited. The James Webb Space Telescope, already revolutionizing exoplanet science, will soon turn its golden eye toward worlds like K2-18b, hunting for the atmospheric fingerprints of forests, algae, or something beyond our imagination. And let's not forget the dark horses, missions like Dragonfly, set to soar through Titan's methane rain, or the daring probes designed to plunge into Venus's sulfuric clouds. Any one of these could transform speculation into certainty, delivering the discovery humanity has dreamed of for millennia, proof that Earth is just one note in a cosmic symphony of life. So stay curious. The greatest revelation in history might be hiding in data already collected, waiting for the right algorithm to tease it out. Or perhaps it's hurtling toward us now, in the form of a signal from Proxima Centauri, or a microbe revived from Martian permafrost. The universe has spent billions of years scattering clues. Now, for the first time, we're holding the tools to read them. The question is no longer if we'll find life beyond Earth, but when, where, and how profoundly it will change everything we thought we knew. The cosmos is alive, and we're finally learning to listen.